All right, density is a great way to practice unit cancellation. Density is defined as mass per unit volume. So it is a compound unit. It's going to be like grams per milliliter for a liquid. And that'll be most common in this chapter. We might see it slightly different in the gas chapter later on. But it does show us the compactness of matter. So how close together can those atoms get to one another? The closer they can get, the more dense an object will be. As we look at densities, realize that the denser object will sink, a lesser dense object will float. So imagine if we have several things mixed together. So let's pretend that we have a graduated cylinder. And then we toss a few things in. So let's toss in some water. Let's toss in some gasoline. Based on 0.7 versus 0.9, that should tell us that at the bottom will be water. And at the top will be gasoline. And if you've ever spilled oil or gasoline on water, you'll notice that it floats for this reason. The homework's going to ask you that if you have an additional object, like a chunk of gold, you throw in your gold ring, how far will it go? Well, if the density is higher than water, it's going to go all the way to the bottom, and that'll be the case here. So it's going to go all the way down and land in the bottom. Symbol for gold is AU. So just pay attention to densities and realize that heavier densities sink. That's why if you have a lot of muscle, you tend to sink to the bottom of the pool, but if you have a lot of fat, you tend to be a little bit more floatable. Also, when you look at objects, can you realize who's more dense than the other? So when you look at Form A versus Form B, notice that in Form A we have some spaces between our atoms. So we have some pretty large spaces between our atoms. So there's a lot of air, so to speak. Air does have things in it, but there's a lot of empty space, would be a better term. And over here, these are stacked so tightly that there's very little space in between atoms. So that would tell you that this one over here is more dense because it's more tightly packed. There's a joke about density, which weighs more, a ton of bricks or a ton of feathers. The reason that joke is pretty lame is because both are a ton, so both are equal in mass. What that joke is trying to relate to, though, is that a ton of bricks might be the size of a large entertainment kind of stand for a TV. Because bricks are heavy, and that's because their atoms are compact. They're very dense. The reason that birds can fly with feathers is because there's a lot of empty space between those atoms. So a ton of feathers might fill an entire room, whereas a ton of bricks might, fill one little pallet. So that's the reality of density and how close atoms can get to one another. The reason we care about density's definition is because you can't change how atoms stack together. Gold will always stack in a particular way to provide us with this 19.3 grams per milliliter density. That's an intensive property. It's a property that does not depend on how much. Extensive properties, however, those do. So an extensive property just means that you could have a gold coin, you could have a gold bar, you could have a gold chain. And no matter how much gold you have, it's still going to be 19.3 grams per milliliter. So the mass to volume ratio is not going to change. And people like pawn shop owners can take this for granted. They can realize that if you bring in a gold coin and you say, this is gold, give me the price of gold for it, they can say, well, let me check it. If they check it and the density is 12 grams per milliliter, then it's definitely not pure gold. It might be gold plated, but then they would lose a lot of money giving you the price of a full gold coin if it wasn't purely gold. So the density never changes, but the amount can. And that's the major difference between an intensive and an extensive property. A disadvantage of a gold coin, if a pawn shop was to check its density to see if it was real, to see if it was pure, would be that it's not a cube. Cubes are the only way to easily measure volume because you can measure the length times the width times the height. So volume is one of our triangles. You can imagine based on this diagram here, the triangle for it would look like a V on top. You have a length times width times thickness on bottom. So you're really just measuring this side versus this side versus this side. And for a cube, those are all measurable with a ruler or any kind of measuring device, really. And that's how we would find volume. You could get mass on any balance, and most pawn shops would have those. The major disadvantage, though, is what if it's not a cube, like a gold coin? Well, then you can get volume by displacement. So if you were to drop a gold coin into, say, water, so here's your gold coin, you drop it into water, the amount of water that overfills and runs out can be measured, and that can be volume instead. No ruler required. So the amount of volume change in water is based on the object submerged in it. And that's an easier way to get volume if you have a irregular shaped object. So let's try a couple density problems. I like density triangles because if you cover up what's missing, you can very quickly figure out how to solve it. So in this situation here, if we have our density triangle from the previous page, that avoids a little bit of algebra. Density is mass divided by volume. And that's what they want, density. So let's cover up density and see what's left. Looks like mass over volume, so that just means density is mass over volume. So the mass is 4.70 grams. The volume is 10 times 10 times 10. And notice this is 3 sig figs, 3 sig figs, 3 sig figs, 3 sig figs. So our answer should be in 3 significant figures. And because our units are compounded, we had grams on top, we have millimeters now cubed on bottom. So grams per millimeter cube is what we're going to be looking for. Very similar on the bottom, we have density is mass over volume. We have 500 grams. We have 150.5 milliliters displaced by water. There we get grams per milliliter. And notice here we have 4 versus 4. So we're going to want 4 significant figures in that answer. So it's just tossing those numbers into your calculator. Making sure that, in this one in particular, that you have parentheses underneath so that those 3 are multiplied before anything is divided. So the main idea behind a lot of these problems is unit analysis. You need to be able to convert a unit, and that's why we're getting you prepared in this chapter for the several chapters that are coming up after it. The biggest problem that students have is they get in a hurry. And when you get in a hurry, you forget what unit you have and you forget that it has to be canceled. So if you slow down and take your time, you can take numbers and divide by other numbers of the same unit and cancel units instead of compounding them. So an example here is 4 hours. How many minutes? So you can imagine if we're using a conversion, if we have 4 hours, we want to be able to cancel hours. So right where we're at here is the same place we're going to be at for the next 3 weeks. If we have a unit hours, it's going to be a whole lot like moles in our upcoming chapters. If you have hours, you need to get rid of it, you need to put it on the bottom because then it can cancel. And that's going to be no different than moles and grams in our next chapter, or moles and liters in our chapter after that, or moles and milliliters or liters in the chapter after it. What we want is minutes. And if we're lucky, we can put that on top. And that's only if we know a relationship between the two. If we don't, we may have to have a second conversion factor to cancel units again. But in this case, we know that in 1 hour there are 60 minutes. And that's enough to multiply and get 240 minutes. So this is called unit cancellation, this ability to have a unit on top and then cancel with the unit on bottom. If you can do that well, you can survive the next 3 chapters. Sometimes the conversions you need are given. The easiest way to recognize that is to realize that if you have the word per, it's comparing one unit to another. If you have a kind of backslash, that tells you that you're converting one unit to another. So look for those clues to realize a unit conversion is in the problem and you don't need any additional information to solve it. So just recognizing that issue of 2 unit comparisons, that's what a conversion is, just like minutes to hours. So sometimes those conversions are within the problem. You just need to know where to look. As we look at 24 hours a day as a conversion, just remember there's 2 ways for any conversion. If we have some number of hours and we need a conversion to days, this is when we decide that hours needs to go on the bottom so that days can go on top. In one day there's 24 hours. But if we were given some number of days, that would determine that days goes on the bottom and that hours goes on the top. The reason this is important is because if we have more complicated problems, they're going to have the same process of, did your units cancel? Yes. And then did the unit that you end up with, days, or in this case, hours, is that what the choices A, B, and C have? If so, then you're done. If not, you may need a separate or additional conversion. Sometimes when you have a compound conversion, you have to do multiple cancellations. So notice here, we started with grams, and we found a way to get rid of grams using pounds. Pounds was part of the answer, therefore we used it as part of the conversion. Once these grams were gone, the numerator was fixed. The denominator was milliliters, so we needed to cancel milliliters. Unfortunately, we needed to go to gallons in the end. So this one required additional conversions. Once milliliters is gone, we went to liters because that's an easy metric system conversion. Then we have liters that needs to cancel with liters. So by canceling those, the only surviving units were pounds and gallons, and that's exactly what we want. So you have to make sure units are canceling or the next 3 weeks are going to be a struggle. The reason we chose to keep chapter 2 until week 13 is to make sure that we gave you practice for unit conversions right when it was important. And we're going to see that with moles over the next several weeks. So to finish intro chem, we have about 3.5 weeks left. So let's show you that multi-step conversion process. So if we have 3.5 weeks left, we need to first get rid of weeks. So we put it on the bottom. And then if we knew seconds to weeks, great, then we'd be done. And that's probably what Google can do for you in about 2 seconds. But you won't have that luxury on the exam. So what you probably know about a week is, in 1 week, there are 7 days. So then we have to get rid of days. And in 1 day, there's 24 hours. And then if you can go from hours to second, great. If not, get rid of hours and go to minutes. In 1 hour, there's 60 minutes. And from there, hopefully you can figure out that in 1 minute, there are 60 seconds. The most important feature of this problem was not that it's a very difficult problem, but it's that notice that we canceled units, canceled units, canceled units, canceled units. The only surviving unit was seconds, and that's exactly what they want, and that's what would be in the A, B, C, or D choices given on the homework of the exam. So just how many seconds are left in the rest of our semester? If this were a 16-week semester, that's about 2.1 million seconds based on the two significant figures that we started with. So the countdown begins. You have 2.1 million seconds to get good at converting units, because that's really all that's left in this semester. So every time you do a unit conversion, make sure you write down the units that you start with, and then you get rid of them. And then you pay attention to the units that your answers have, because that's where you need to end up. They should end up in the numerator. Everything else should cancel in the denominator as you go across. Sometimes you have a compound unit, you might have to convert top and bottom separately. So let's try this last problem and see if we can cipher through the unit cancellation process, because that's really what we're trying to get good at. We have 500 liters. We have 0.00130 grams per milliliter density. They want mass. We could probably cheat off of our triangle on this first and realize that if density is mass over volume, and it is, they want the mass in kilograms. So get rid of mass, and it's just density times volume. So here's volume. Let's multiply it by density. Density is 0.00130 grams per milliliter. That's the way they write that conversion out. Disadvantage is liter and milliliter will not cancel. So what we'll have to do is a separate conversion to say, well, if we want liters to cancel, we'll put it on bottom and milliliters on top. That'll help these cancel, and that'll help those cancel. So in 1 liter, there's 1,000 milliliters. That's 3 columns in our metric table from earlier. We also have grams, but need kilograms. So we're going to need a separate conversion to get rid of grams and go to kilograms. Notice again, grams cancel. Look at your metric table again for this one. Kilogram is bigger, so we'll give it a 1. And then it's 3 spaces to the standard unit. So then we have 500 times 0.001 times 1,000 divided by 1,000. And we'll get our answer. Pay attention to sig figs. We have 3 up here. We have 4 there. We should end up with 3 when we're done. And we do. Last part of this chapter is energy. And energy is just another conversion. The 2 types of changes we talked about in week 1 show us that energy comes in lots of different ways. Typically, though, energy is going to come in heat or light. Energy is defined as the capacity to do work, so you can imagine when you eat food, you have the capacity to do work. So one of the most common places for us for energy is the calorie. Calorie is one of the most well-known units for energy, and it's related to joules in the SI system. You can convert calories to joules based on the 4.184 conversion at the bottom. So, speaking of energy, if you want to be able to calculate energy of, say, food items, you're going to have to know how much heat they can transfer. So, if they can transfer energy to your body, they can transfer heat to, say, water. And if we know the specific heat of water, namely the amount of heat needed to raise 1 gram of water by 1 degree Celsius, we can say that if there's that much calories stored in the food, that's how much our body could take advantage of potentially if we digest it and absorb it. So here's a list of specific heats at the bottom. Water is the standard at 1. It's a very high number. That just tells us that water takes a tremendous amount of time to heat up, but also a tremendous amount of time to cool down, which keeps our planet pretty moderate in climate. Disadvantage of metals, as you'll notice, is their specific heats are very low. That means they're going to heat up very quickly and cool down very quickly, which makes them great for cooking, not so much for the surface of a planet, because that would heat up way too fast and cool down way too fast to support life. As we look at a calorie meter, called a calorimeter, we can look at the ability to put food inside like a Twinkie, blow it up in this bomb container with oxygen, and all the carbohydrates and proteins and lipids that are stored inside are burnt, and their energy is transferred to the water around it. We can measure the energy transferred by a thermometer and then calculate the amount of energy hiding inside. So any food item has to go through this process for FDA standards to give us an idea of how much calories we're eating, so we can calculate how much food we can eat without getting fat. In reality, this is just one more unit conversion. So this is our last triangle of our handout given in class. But it's a triangle nevertheless that just shows us that we can avoid algebra if we use the triangles. So Q equals mass times specific heat times delta T. Q is calories, that's energy. Mass is grams. Specific heat comes from that table. And that's calories per gram times degrees Celsius. And then delta T is change in temperature, that's temperature final minus temperature initial. And that's in degrees Celsius. Notice grams will cancel, Celsius will cancel, and calories will cancel. So in these problems, you're going to see a few of them, not many, but you're going to have 4 variables, 3 given, 1 you solve for. So in this situation, it says, what is the energy? Energy is Q. So cover up Q. That's just those 3 numbers multiplied together. So Q equals the mass of the water times the specific heat of the water times the change in temperature of the water, all caused by the incinerated Twinkie. So Q equals the mass of 1.00 times 10 to the 4th grams of water. That's the surrounding water around the bomb where the Twinkie was incinerated. We have the specific heat, which is the conversion factor. That's 1 calorie per gram of water times degrees Celsius of water raised. And then we have the temperature change of 45, subtract the initial temperature of 25 Celsius. So notice grams cancel and calories remain, and then Celsius also cancels. So calories are left over. And as we multiply 1.00 times 10 to the 4th times 1 times 20 would be the difference here. You get 20 times 10,000, that's 10 liters. And then you get 200,000 calories. Which seems like a lot, right? That's a lot of calories. That's a lot of energy. But this is lowercase calories. If we want to get it into food calories, there's a mind trick that our famous government does for us. They go from lowercase calories to capital calories to make that number not seem so scary. So in 1 capital calorie, there's 1,000 little calories. So really a food calorie is 1 kilocalorie. And that tells us that a Twinkie really has 200 when they label it on the package. And that's to save us from ourselves. If we knew that calories have 200,000 calories, we wouldn't eat them. And I'm telling you that they do. That doesn't mean you can't eat Twinkies, because Twinkies are good. It just means that you need to pay attention to what you eat. Because if you have a 2,000 calorie diet, you really have a 2 million energy calorie diet. And that's a lot. So when you think of numbers, think of what's significant. Here we started with 3 and we ended with 3. And if you can keep track of sig figs, you're pretty safe in this chapter. And if you can cancel units, you should be pretty safe in all the chapters coming up. See you next time.